Conductors, semiconductors, and insulators. By the end of this lesson, you should know the structure of the atom, know how conductors, semiconductors, and insulators work in terms of electrons, and know what is meant by an energy band. Let's take a look at a basic structure of the atom. At the center of the atom, we have the nucleus. The nucleus contains two particles. The first one, known as the proton, has a positive charge. The second type of particle is known as the neutron, and neutrons have zero charge. Orbiting around the nucleus, we have particles known as electrons. The electrons have a negative charge, and they exist in areas known as shells or bands. Looking at the shells or orbitals in more detail, the very first shell can hold 2 electrons in total before it becomes full. All of the other shells have the capability of holding 8 electrons before becoming full. The outer shell, which is also known as the valence shell, has the capability to hold 8 electrons, but in this instance, it is not full. It only has 1 electron. In this instance, we're looking at potassium, which is a metal, which is a very good conductor, and this 1 electron in the outer orbital will actually become more significant later on as we go through the lesson. Now imagine these shells or orbitals have actually been laid out flat. And right now we're taking a look at our electron. When the electron exists in the ground state, this is the state which is closest to the nucleus, it is said to be in a state of rest. Whenever it starts gaining energy, it exists in these excited states. Whenever the electron gains enough energy, it reaches its outermost orbital, and it can technically leave at this point. The outermost orbital is also known as the ionization level. Now you may remember that an ion is when an atom gains or loses an electron, and it becomes, in this case, positively charged. Because we lose the electron, it leaves a positive charge behind. Whenever the electron leaves, we have conduction. So to summarize so far, the atom consists of a centrally positively charged nucleus with electrons orbiting the nucleus in fixed orbits. These orbits are sometimes called shells or bands. When we are considering these orbits, we will often regard them as energy levels, and we say that the electrons occupy energy levels inside the atom. Electrical properties of an element will depend on the number of electrons in its outermost or valence shell. Now you may recall that earlier on I did mention that potassium having 1 electron on its outside orbital would be significant. It actually determines what its properties would be in terms of conductivity. Now we have something similar to potassium. Over on the left hand side we have an atom with 1 electron on its outside shell. In the middle we have an atom with 4 electrons on its outside shell. On the right hand side we have an atom with 8 electrons on its outside shell. Now, technically, the better conductor would be the one with 1 electron, and this. Metals have a low number of valence electrons, and these are easily removed from the atom. This means that metals are good conductors. Because there's only 1 electron, it's sort of loosely bound to the atom, and there is less stability. You get more stability the more electrons that you have in this outer orbital. Now in the next one, non-metals have 4 or more valence electrons, and they're more tightly bound to the nucleus. They're much harder to remove, and it makes them very good insulators. Now we'll go into more depth with this as well too as to why this makes them good insulators. But over on the right hand side, where we have 8 electrons, we have a full valency shell, so it's very stable. It's very difficult to remove any electrons from this shell. Elements that have a full valency shell are very, very good insulators. This means that in metals, the highest occupied band is not completely full though, and this is known as the conduction band, which we'll talk about later on. And that's the first unfilled band above the valence band. So if non-metals have 4 electrons in their valence shell, why are they more stable? Now if you take a look, here we have 4 electrons around a silicon atom, and they're technically sharing electrons here. The atoms are covalently bonded with each other, which means that they're sharing electrons to form full outer shells and become more stable. Now if you count it up, you can see there's actually 8 electrons around the silicon atom, but 4 are its own, and 4 belong to other atoms that they're covalently bonded with. So technically they're sharing electrons, but because they have the full outer shell now, even though it's shared, they're technically more stable. Now let's focus on band theory. You heard me mention before this term conduction band. Now, conduction, as you're aware, is when the electrons are allowed to flow. We've also discussed the outer shell, the valence shell, which contains the electrons. What we're going to do is we're going to focus on the right-hand side here. Over here on the right-hand side, you can see there's a conduction band and a valence band, and there's a bit of overlap between them. In conduction, we know that the valence band is not completely full, and the electrons are easily removed from the atom because of this. Because of the overlap, the electron only requires a small amount of energy to move from the valence band into the conduction band and allow conduction to take place. Focusing on the middle diagram now, we have what's known as a semiconductor. The valence band and the conduction band have an energy gap. Now this energy gap is quite small compared to what we'll look at later on. And in semiconductors, the energy gap must be jumped by an electron for conduction to take place. Only by gaining energy of some form can the electron go from the valence band to the conduction band. Most of the time this energy is in the form of heat. It's also known as thermal excitation. Focusing on the diagram on the left-hand side now, we have what's known as an insulator. And you'll notice that the energy gap between the valence band and the conduction band is significantly greater than the semiconductor. Now, normally it's impossible for the electron to cross this energy gap. It cannot actually receive enough energy for it to happen. So when you do give the electron some energy, it might go so far, but unfortunately, it won't be able to cross and it will fall back into the valence band itself. Check out the link above for animations involving band theory and conduction. Some key points to note. In solids, permitted electron energy levels are organized as bands. The valence band contains electrons that can be considered to be bound to the atom. In insulators and semiconductors, the valence band is full. The conduction band is a region of permitted energy levels that is empty in insulators and semiconductors, but partially filled in conductors. Only partially filled bands may permit conduction. There is a forbidden zone that forms an energy gap between the valence and conduction bands in insulators and semiconductors. That energy gap must be jumped if an electron is to move to the conduction band, and this is not normally possible in insulators because the gap is too large. In semiconductors, the forbidden zone is much smaller and electrons can jump the gap to the conduction zone as a result of thermal excitation.